Okay, problem number 3, writing repeating decimals as geometric series using sigma notation and then finding its fractional equivalent. So let's do this first one here, 0.4242424242. This must be the answer to all of your problems. What can we do with this number? Well, the trick for working with these repeating decimals is to think of each repeating part by itself. So think of the first term as 0.42 and think of the next term as 0.0042 and then the next one 0.000042, etc., 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 etc. each time. Because if we smushed all those together, we'd end up with 4.42 dot 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 forever. So think about these as fractions. That first fraction, 0.42, well, that's just 42 over 100. Then this next fraction, 0.0042, well, that has 2 more zeros in it, which means my denominator needs to have 2 more zeros in it. Same thing for that one, 42 over 1, I need 6 zeros. And then same thing with that last one there, I have 1, 2, 3, 4, 5, 6 zeros there, and so I need 8 zeros down here. 1, 2, 3, 4, 5, 6, 7, 8. But the key is each time I'm increasing the number of zeros by 2 in the denominator, which means that's like I'm multiplying by 1 over 100. And there, same thing, multiplying by 1 over 100. And again, multiplying by 1 over 100. So my first term, if I'm writing in geometric sequence here, a sub n equals my first term, which is 42 over 100, times my ratio r, which is 1 over 100, to the power of n minus 1. And so I want to calculate the infinite series of this, so the sigma from n equals 1 up into infinity. And so to do that, my infinite sum will equal my first term, which is 42 over 100, divided by 1 minus my ratio, which is 1 over 100. And we can simplify this. 42 divided by 100 over 1 minus 1 100th is 99 100ths. And look, my 100s will cancel out, and I'll be left with 42 over 99. So 0.424242424242 forever is 42/99. And I can do the same thing up here. The idea is going to work the exact same way. I'm going to be looking at a infinite geometric series. I am going to have, my first term be just the part that repeats. So 135 over 1,000, because that will give me 0.135. Notice that the number of digits is the same as the number of zeros on that bottom there. And I will multiply that by my ratio, which will be 1 over, well, how many zeros do I need to add each time? Well, I need to add 3 zeros each time, raised to the power of n minus 1, which then I can calculate by taking my first term, 135 over 1,000, and dividing that by 1 minus my ratio, which is 1 over 1,000, which will give me 135 1,000ths divided by 1 minus 1 1,000th is 999 1,000ths. And so again, those cancel, and I'm left with 135 over 999, which is that repeating decimal right there, which is cool. And then same thing here for this last one. This time, it's just the 7 that's repeating. And so I can find the infinite sum from 1 to infinity of my first term, 7 over 10, 1 digit, so 1 0, times my ratio, 1 over 10. I'm moving by 1 0 each time, raised to the power of n minus 1, and it equals, again, my first term, 7/10, divided by 1 minus my ratio, which is 1/10. And so I get 7/10 divided by 9/10. The 10s cancel, and you're left with 7 over 9. So look at each of those numbers. When we had just a 7 repeating, it was 7 over 9. When the 135 was the thing repeating, it was 135 over 999. When the 42 was repeating, it was 42 over 99. In each instance, the fraction worked out to be just the thing that was repeating in the numerator, divided by however many digits there are, that many nines. So that's kind of super awesome. And there you have it, writing repeating decimals in sigma notation.